Hi all, and welcome also from my side. So what I'm going to tell you about today are the absolute basics of machine learning. So this is the stuff that we really hope you know already, but perhaps it doesn't hurt to put everyone really on the same page and to re-review some things that might have fallen back. So if we begin where it all starts and look at what often happens during scientific experiments, well, you observe a phenomenon and then you try to construct a model that explains it. And then to make sure that your model really explains it, you make predictions from the model and hope that they would fit the other observations of the same phenomenon. So the difference in that with what machine learning is trying to do is that here the model is constructed automatically. And to be more precise, this is the comic that illustrates the problem really well. Basically, it's all true, right? So we do put all the training data that we have, so all the observations of the phenomenon that we have, into a gigantic system. So if you take the modern methods like the deep learning, the convolutional neural networks, it's just a gigantic pile of linear algebra, and then we try to tune it until it actually works. So if we go back though, yes, and say step by step what actually happens. So we define a model with parameters. It doesn't have to be a CNN, right? It could still be linear fitting. That would still be machine learning. So it has a very different range of parameters from 1 to millions. We estimate the parameters from the observations we have, and then we validate the model predictions. And here, just to introduce some terminology, the observations that we use to estimate the parameters of the model are known as the training set. And the other observations on which you validate the model predictions are known as the test set. And this is really the key point of the whole endeavor. So if you remember one thing about the basics of machine learning, this should be the thing you remember. That completely, totally separate the training and the test sets. So never train on test data, never test on the training data. The reason why it's so important will become apparent in the next slides, but for now, just recall also that you have to take it very far, right? If your data processing pipeline is not just the little machine learning algorithm you have in the middle, it actually applies to everything. If you have some pre-processing, only estimate the parameters of the pre-processing from the training data. If you have some post-processing, remember that you can only estimate the parameters of the post-processing from the test data. So you have to post-process not the model predictions on the training set, but the model predictions on the test set. And then if you have a pipeline like this, which actually involves multiple parameter estimation steps, you have to introduce additional validation sets on which you will validate the complete pipeline. So suppose you did all that, and now let's look at what could actually go wrong. Well, the two main problems there are underfitting and overfitting. Let's look at both. So the underfitting is, in a way, an easier case, right? So this happens when the model just cannot learn to represent the training data. The example that you see here, you can also clearly see that no matter how much training data you actually throw at it, the line will never fit the curve. So you can fairly easily find the underfitting cases like this by just examining the error the algorithm still makes on the training set. If it's not improving as you add more training examples, your model is not complex enough, it doesn't represent the data. Now, the more dangerous problem, or rather the one that is kind of harder to find, is overfitting. And this is the case when the model learns to represent the training data too well. So on the training set, your error is actually going to be 0. However, on the test set, the error is going to be quite high. So in the right plot, you can see the test set as green stars, and you see that there the model predictions actually deviate from the true observations quite far. So now imagine that you actually didn't separate the training and the test set properly, and some of the test points actually seeped into the training set. So on the one hand, yes, maybe it would have fit better if it was underfitting before. On the other hand, you would have never caught any overfitting errors because the error on the training set is 0, because it learned to represent everything it has seen in the training part already perfectly, right? It adjusted itself to every little noise point in the data. So if you want to detect the overfitting errors, you really have to keep the test set cleanly separate. And there you will also be able to see that, and you will see it also in all our hands-on sessions as you will be training your own models, that the training error keeps improving, but the error on the test set or on the validation set is not going anywhere. So this is the case where your model just stopped getting any better. It stopped generalizing, it's just overfitting. So I think we will see a lot of that in the future, but for now, let's go on. So in the statistical learning theory, this kind of a balance between underfitting and overfitting is known as the bias variance trade-off. And the situation that you have on the left, so the underfitting one is the high bias, right? And the one that you have on the right is the high variance. Right, so can you actually drive both of them down to zero? So we know that this is actually not possible because, well, there is irreducible noise. And so you can drive it down some, but not all the way. So you will never represent the underlying phenomenon perfectly just because there is the noise in the model. So what can you actually do against overfitting? So against underfitting, you just have to change the model. Against overfitting, the most popular method is perhaps regularization. So this is a very broad term that describes a lot of different techniques. But roughly what you can say about how it works is that, well, you usually have a certain loss function, which we will stop on in more detail later on. And this loss is your estimate on how well the model is performing. Right, so the popular losses for regression is, for example, mean squared error. Or for the classification problems could also be the misclassification rate. So what we mean here by saying regularize is that, well, in the loss, if you just take the mean squared error, this is the term that describes how much it deviates from the data, right? This is the data dependent part. You can add another term which will depend on the parameter values and will penalize too much flexibility. So if your parameters are not as flexible, they will not be able to create this kind of an oscillating curve that we had in the slide before. So there are many methods that people have developed over the years to regularize. The most popular ones are perhaps the L2 regularization, which keeps the parameter values low, and the L1 regularization that keeps the parameters sparse, but there are many others. Right, so another method to somewhat combat overfitting is the ensemble approach. So that is, for example, the popular random forest classifier. And what it comes to is you train multiple models on random subsets of the training data. And then even though each of them could be more biased because it doesn't see enough, but then when you average their predictions on the out-of-bag samples, it actually performs better. So the very popular question that we get asked a lot is how much training data do you actually need? And this is impossible to answer without the problem at hand, right? So you need as much as needed to describe the true data variability. Your model will only be as good as the training data, but you can't really say here. So, well, you will see when it stops converging. That's about as well as we know. To summarize the whole thing, well, the supervised machine learning deals with fitting models to observe data based on the examples. Underfitting and overfitting can both be caught by examining training and test set error. And well, if you want to reduce overfitting, that can be helped with the regularization approaches. That's it for this part.